little too
All right,
much.
guys, while you are copying this down, if you want to take a picture of this, I will post this to the Dropbox so you can get it off of that if you want, but you can take a picture of it and you're perhaps, if not hating me, maybe not loving me as much as you've learned to love me in this class, I hope, because of all this homework. However, there's some silver linings here. Firstly, we have a 4-day weekend, and we can do that. Reminds me of the old joke, where you're, thank God it's Friday, only 2 more days left in the work week. That's what we used to say when in my old job, working weekends. Plus, some of these problems are pretty quick. 7 through 10, matching a graph to a function, and the 111 through 114, true and false questions. So, pretty quick questions. You have to think a little bit about them. Make sure you think about them, because it was a good set of problems because it reinforced a couple of concepts and might catch you from thinking the wrong way about it. So hopefully steer you in that direction. Wednesday, I probably will not be here. You might not be here either, depending on the weather. However, I understand Mrs. Hendershot will cover the class. And so what I want you to do is work together to go over these problems, which you should have completed by then. They'll go pretty quick, I think. It's a lot, but I'm trying to press us forward here a little bit. And then secondly, do a couple of free response questions, which will be in this folder. Set it next to the pencil sharpener here, labeled Fun Calculus Problem. Well, you be the judge. They're fun. I shall send them over there right now, so don't forget. But free response problems, work together on those also, and help each other out. As you try them yourself first. Always try them yourself first. But if you get stuck, you want to get a little hint, a little bit of help, then ask your friends and colleagues here in the class. All right, a lot to cover today, so let's get into it. Yesterday we answered the million-dollar question. With that answer, you might say, well, who needs the rest of this? Let's just go straight to the $1 million. But we did determine it still takes 46 years to get there.
In A in calculus.
And in A in calculus, and that leads to the second $1 million question, which I will show in a minute. So what we're going to do today, find derivatives of functions involving logarithmic functions, natural logarithmic functions in particular. And it turns out this is actually pretty easy. I think you guys will get it pretty quickly. We want to do a lot of practice with it. It's different forms, but I think you'll see the fundamental concept is easy, matches up very nicely with derivatives of like trigonometric functions that we take in the past. There's some similarities there. So let's jump right into it. Any questions at all from yesterday? I think you guys knew the definition of logarithms. I was pleased that you had a pretty good understanding of it. This is what we showed yesterday. Logarithm base b of y equals x. That means, what do I need to raise b to get y? B raised to the x equals y. And that's really if and only if b raised to the x equals y. And that's the concept, that's the definition, that's the approach here. In calculus class, we use a base of e. You'll see why here in a minute, because taking the derivative of the natural log is pretty easy. We want to do that. Plus, it matches up with things in nature and problems that we want to do. So it's much easier to do that. Natural log of e, so here's a quick quiz, is what is the answer to this? Everybody have the answer? No. All right, let me ask the question differently. This is, oops, let's put this on. All right, this is log base e of e equals e raised to the what power equals e, and the answer is, everybody,
1.
Holding up one side, this is 1. So that's good. And we'll want to know that because we might get a function that's e to the 2x plus 3 or whatever, and then we'll want to take the natural log of both sides, natural log, right? And that'll allow us to bring, using the other rule, bring this down over here, get it down to earth, right? We get it where we can use it. And then the natural log of e part is 1, that goes away. If it weren't natural log of e, if it were natural log of 3, well, we just keep that, that's all. We can still bring this down, but that doesn't evaluate to 1. Natural log of 3 is something different. I don't know what the answer to natural log of 3 is. Let's not think about that. Let's just move on. We can use our calculators. Graphs of logarithmic functions and exponential functions. Some familiarity with this. You guys should know what these look like in general. The other thing about these is transformations. I almost wonder if we do enough transformations in math. If you guys have seen it in Algebra 2, pre-calculus, where you start with a function and then you're moving it right, moving it left, moving it up, moving it down, amplifying it, shrinking it, changing the frequency for trigonometric function. All those types of things will change the shape of it. We want to know how to do that. I think you guys know how to do that. For example, natural log of x plus 2 brings it up 2, and so on and so forth. We put a minus sign, we flip it up. So those things. Domain, what's the domain of the natural log function? What's that look like? What can we put into this function? What do you think, Joel? Well, it's right there, isn't it? 0 to infinity, right? But not, so positive numbers, not negative numbers. So you can see from the graph, you can put in, what can you get out of it? Well, you get out of it, it's the range, all numbers. It actually looks like, you might think this is going to hit some horizontal asymptote. It doesn't. It just keeps going. Keeps going up to infinity. Function is continuous, increasing, 1 to 1. Heard that concept before, meaning you put x into it, your value of x, you get one value of y out of it. And that means there is an inverse function. If you had a function of x squared, it's not 1 to 1. You can get 2 values of y, right? And the x squared fails the horizontal line test. The vertical test for a function, horizontal test for a 1-to-1 function. The graph's concave down. All right, so that's the sense of that. Let's move on. Properties we talked about yesterday. Turns out your textbook reviews these properties too. The calculus textbook reviews these properties too. This table was taken directly out of your textbook. These are the same. The variables are different, but the properties, of course, were exactly the same. We can use any variables we want. And these are things we learned about yesterday. Hopefully you can apply today. Any questions about these? Be aware that the natural log, the log of a plus b is not equal log of a plus b, right? People make that mistake sometimes. They think, oh, log of a plus b, that's equal to the log of a plus b. No, the product of a and b is equal to the sum of log a and b. It's kind of a common mistake that people make from time to time. Okay. The other thing to mention here is you'll hear me do this sometimes. Often I say natural log, but I may just say log, and you'll see it's ln, the n telling us that it's the log of base e, but you hear a lot of math teachers, professors, and so forth, will just say the log of this, and if it's written ln, it means the natural log. If it's written log of some other base, it's whatever base is shown there. It's implied what they're talking about, which is to say you don't always say natural log. Say a few words. Okay. Let's come back. I think you guys can do this. Let's do this. See if we can do this. Actually, try this one yourself. Expands log base 6 of 5x cubed divided by y using our properties of logarithms. Give that a go.
That's what I got.
Parentheses around new, which one?
The first two. I don't know if it matters.
No. No, we're okay on that. If there were a product down here, you want to put parentheses minus the bottom part so you don't lose the product. But does that match everybody? What you said? Note that this is not 5x all cube, it's just the x parts cube. Otherwise you pull the 3 down first and then break it out.
So you don't need to put a parentheses around the.
No, here,
Yeah, no.
what are you thinking, here? Will?
Yeah,
No, why do you think you might need to do that?
because when you were splitting up the, like, because y in the original function is you're dividing by both the by both the 5 and the x. that you
Oh, I
can
see
go up.
why you're thinking that.
Yeah.
No, the answer is no, you don't need to do that.
Why?
Well, this follows the rules of subtraction, addition, and so it's not going to evaluate
It
any
doesn't
differently.
matter. Yeah. Okay.
You won't evaluate
Okay.
any differently when you do that. So here's another one we can, this one is expand, this one's compress. Get close eye on the clock. Let's not do this one. Let's move on. You guys can do this, I think.
Yeah.
Look at. I want to make sure we get to some other things. Here's the other $1 million question. Differentiate this. And you're looking at that and thinking, holy crap, or worse to that effect. Because even without the natural log, you have a product rule, you've got a quotient rule, you've got a power rule, you've got a chain rule, you've got everything embedded, and throw the natural log on top of it, and life looks pretty bad, doesn't it? But there's a silver lining. The silver lining is that with the natural log, it actually makes the problem just a little bit easier. And we'll see that. And it's hard to believe. But here's what you need to do first in a problem like this, and that is to expand it. So use the function, use the logarithmic properties that we've learned, and expand this to make it a sum and a difference. Actually, why don't we take a minute to do that? See if you can do that, and I'll do it. We'll compare notes. We'll see if yours matches mine. So expand this, natural log of that function. I'm going to do it over, stand over here so I can run out of space. Let's see. Match? You guys match up to mine? My writing's not great. I think that works. That works. Yeah? Good. It's, when you do, you practice this a little bit, and you can do it, you can roll right through it and do it in one sweeping. But before that, while you're refreshing your memory, you might want to do it one step at a time. Say it's this piece, then this piece, then this piece. And I kind of laid it out that way. Then we say take the derivative of this, and we'll learn how to do that right now, actually, this part. But we want to spread it out this way. You don't have to, but it's easier, and you'll see that here in a minute. So, recall the general power rule. There's one case that it doesn't apply for. Remember that? I went over this really quickly when we were doing this. And I said,
X
well,
to the negative
this is
1.
actually equal to the natural log of x. When n equals minus 1. Why is that? Because it's 0 in the denominator. And so what do? Well, you create, if you're in the math world, you create a new function that is unique to resolve that particular circumstance, which is what they've done. Our friend Newton, or maybe Leibniz, one or the other, did that. So here's the function. The definition, this is the calculus definition of the natural log function. natural log of x is equal to the integral from 1 to x of 1 over t dt, and x is greater than 0. It's positive. X is positive. Again, it's positive because you don't take logs of negative numbers. So what does this look like when you guys see this? Let me ask a different question. If I said, take the derivative of this function, what would you tell me the answer is? I say derivative of natural log of x dx is equal to derivative with respect to x integral 1 to x of t dt. It's really noisy, isn't it?
Yeah.
Yeah.
It's a lot different now. It's turned off.
I
Yeah.
feel better. We're going to leave with headaches.
Huh.
All right, what does this look like?
Second fundamental theorem of
Everybody
calculus.
That
agree with
one.
that? Yes.
I agree.
Second fundamental theorem. So what is the answer?
One of us.
1 over x is an easy one. We
Yeah.
have conveniently a constant in the lower limit, a variable. The variable is just x. It's not something else. And so the answer is 1 over x. And there we have the general solution of the derivative of the natural log of x. Almost deserves an applause here. Maybe, Jeremy, I don't know. No, I was thinking. Okay, a small one. Will's going with it. Derivative of the natural log of x is equal to 1 over x. 1 over x. That's better. And it turns out that, of course, the chain rule applies here too. And so let's take a look at that. Here it is written, same thing, we just did derivative of natural log of x is 1 over x. And this is u be a differential function of x. This is a statement that says the chain rule applies here. 1 over u du dx is equal to u prime over u, and u greater than 0. You're looking a little confused here.
Yeah, I need to see that in a
This is
problem.
the,
Again,
it's the
every-
notation here, but this is
Oh, wait,
outside
okay, I
function,
think I get it.
inside function. Outside function is natural log,
Oh, okay.
outside function is the outside.
Oh,
This is the
oh, okay.
I get
It's
it.
just the derivative of the.
Yeah, correct. And we'll look at that here in a minute, and you'll see, oh, I get it, it's obvious. But this is the notation that's saying the chain rule applies here. The chain rule. Question, Jeremy?
Yeah, is there a little comma or dots or?
Yes, that's the derivative.
No, I mean the denominator.
Yeah.
That's a comma.
That's a comma saying, that's a comma.
That's an annoying
Saying,
thing, though.
yeah, it is. Cross that out. Does that help?
Oh.
Yeah, that is funny, though.
Can erase that. It does create a little bit of confusion. That's a good question.
Yeah.
But let's look how it works, because this fits our old and loved model of chain rule. And so let's just do this one together. Natural log of 2x, derivative of natural log of 2x is what do you think?
It's 1 over 2x
Yeah, keep going. 1
And
over
then-
2x
times 2.
times 2 is equal to
So you get 1 over x.
1 over x. Yeah, easy, right? We can do that. Let's bring them all up. We'll do them fast. Slightly trickier, but not much. Derivative of this one, anybody volunteers to knock that one out? Michael?
2x over x squared plus 1.
You did so fast. So we'll start with the 1 over part. I always like to start with the 1 over part. 1 over x squared. You guys, see, my brain's older now. It's not as fluid and fast as the youthful brain. So I'm going to do it this way. 1 over x squared plus 1. And the inside derivative is 2x, which is what you just said. I know, but I'm doing it the slow way, the methodical way, right? 2x. Make sure it doesn't look like it's 12. Did everybody agree with that?
Yeah.
Right? Yeah? All right. Derivative of x times the natural log of x. Jeremy's going to give us one to go.
Is this equal 1?
Just equal to 1. Or walk me through the steps here. You guys can't do that to me. All right, it's the product rule, right? It's the
Yeah,
product.
1 over x.
Derivative of the first, let's say derivative of the first 1 times the second, natural log of x, plus derivative of the second, 1 over x, times the first, x. And we can simplify that, right? So x over x, that's the 1. I think it's natural log of x plus 1, right? Natural log of x plus 1. Is that right? Yeah?
Yeah.
Good. I'm not sure that's what you said, or maybe it was.
Yeah, that is what I said.
It is what you said. Okay. All right. I caught up to you. Thanks. You guys are going fast. That's good. I'm glad. We can do all this homework. The homework's going to go fast for you. All right. And then last one. Somebody tell me. John, just tell me the answer. I mean,
I
Or you
don't
wanna go
know
to the
the
steps?
answer. Yeah, the steps.
Let's do the steps.
let's do the steps. This is a little
Do
tricky.
you have to do like
Yes.
ln of x times, like do a
What?
product rule of,
Yes.
You split them up.
yeah.
Think of it as now the outside function is the cubing, right?
Okay.
And then we work the inside function. So what do you think?
You have to move
Oh, so it'd be like 3
squared.
3,
times like ln of x, natural log of x squared
right?
times 1 over x.
Correct.
Okay. Or over x, yeah.
Yeah, this is a little bit tricky because it's not, this isn't saying the natural log of x cubed. It's not that. It's the natural log of x all cubed. And so it would be a different answer if it were. This is obviously different.
And so if it doesn't have the parentheses there, it just means that. Is it gonna do parentheses like that? Or is it just
No, it'll be clear on it. I see what you're saying.
Yeah, like-
Might it show
like I think it'll be obvious if it's like the whole thing is cubed, but then I think that's how they'd write
Here's
it for
what
x
they'll,
squared.
correct.
Yeah,
That's correct. If they want this,
they'll write
then
it.
they'll do this. And if they don't want that, they'll just take the brackets off. I think we'll
Yeah.
see it that way. Yeah. That's a good one to do. All right, you guys are off to the races here. So we're back to our other $1 million question. Let me go back to our expansion of this, and if we can get there. There we go. No.
No,
I think it's a
you were
couple
going the right
further,
way.
Yeah.
Okay, here we go. So now, so you can see, you want to take the derivative of this one, right? And so you could say, well, it's 1 over all this stuff times the inside derivative, then you're back to taking the inside derivative like this. Or you could expand it, like we've done here, and take them one piece at a time. And I think we can see, a lot easier to expand it and now take them one piece at a time. This problem becomes easy. Let me write it a little bit more neatly here. Natural log of x plus 2 natural log of x squared plus 1 minus 1/2 natural log of 2x cubed minus 1, right? So I just rewrote the expansion that we did, logarithmic properties. And now we have to differentiate this. And that's the same as what we just went through, 1, 2, 3, right? We can do that. Don't get caught up by the constant. The constant is constant. We can always take the constant on the outside, right, and just deal with the other part. So this one's easy here, right, Joel?
No, whatever it is.
Yes, 1 over x here. This one, what about this one here, this part? 2 natural log of x squared plus 1.
4x over x squared.
You guys, it's always skipping the steps, but that's okay, you're right. I just,
Yeah.
yes, 4x, 2x over x squared plus 1. Yeah, is that right? That's
Yeah.
good, that's okay to skip steps. And then the next one, anyone, Jeremy's gonna give that one a go?
Yeah, 3x squared over 2x cubed minus 1.
Yeah, and all the combined steps here, 3x squared
Over 2x cubed minus 1.
minus 1. So we took the inside derivative 6 x squared divided by 2 is 3x squared.
Oh, that's good. Okay.
So 6 squared.
And we're done. What? Oh, sorry, what? No.
6x squared.
No, but the,
No, but
1/2.
yeah,
One half. See, this is.
That's why it's skipping steps.
I
is
know.
not- yeah, no, I'm probably gonna end up writing all those steps.
I like it, yeah. You can skip once a
But I
little bit here,
understand.
but doing it all in your head, you might miss the 1/2, right? You didn't. You got it exactly right, so that's good. All right, so not too bad. All right, I'm gonna run out of time, all right. Let's see, we've come a long way. We got this, I think. We're gonna do well on this. We did that. Yeah, we really did it. here's two things. I'll let you look at this yourself. There's example 6 out of your textbook. It's a concept called logarithmic differentiation, which sounds harder, and it's frankly a little bit unclear to me whether it's easier or not. In some cases, it will be easier. Here's the concept. You have this function, y equals x minus 2 squared. You can take the log of both sides first, right? Take the natural log of both sides first, and then expand this side like we just did. Then take the implicit differentiation.
I guess it's like if you don't like to do the quotient rule,
and all
then
the
it's
rules that
easier.
are embedded in this.
Yeah.
You space it out, and it's easier. Maybe, right? Take a look
It's
at this.
more writing,
Useful.
probably.
One last thing, it's a quick one to show you, but I do want to make you aware of it. This one's going to be quick. It's close. You could maybe time yourself and do it one way
Yeah.
and do it the other. This will require implicit differentiation, by the way, because you're taking the natural log of y. So it'll be...
So that might be harder.
Well, that part's, the implicit part on this side is easy, right? So it's going to be
It's just gonna
1 over y, dy
dy
dx.
dx.
All right, let's keep going. One other piece. Example. Okay, last piece. So we can only take logs of positive values. So the natural log, you'll see this, natural log of absolute value of some function u. And that's just same, it's a chain rule, right? 1 over u times the inside derivative. Let's take a quick look. One example. So this is easy, right? You see this, you might get a little bit alarmed. You've got the natural log of the absolute value of cosine x. Take the derivative of that. U prime over u. Outside, it's the same thing. Natural logs on the outer function.
No, it's just saying let u be
so
the
u is
middle
the
thing.
cosine.
So you take the derivative of that and then
Correct.
put the other thing on the denominator because that's like 1 over x.
Correct. It's the same. This
Yeah.
is the chain rule all over again. So I'm trying to go too fast, right? And this is what happens. 1 over cosine x. That's this piece times the inside derivative of cosine. The derivative of cosine is minus sine. That's this piece, right? Outside function, inside function. And we can simplify that to the tangent function. That's all. So don't be alarmed. It's the same thing. Don't be alarmed with the absolute value signs. Okay, good. We made it.